This is Unit 4E. It deals with radioactivity, describing it, and specifically half-life. So hopefully we're quite familiar with the bedrock ideas here at the bottom. Matter, we've got our nucleus there. It's the nucleus we're interested in. Electrons are to do with chemistry mostly in this context. So what is happening in the nucleus? Well, there's two basic processes we need to know about. The first is alpha decay. Now, decay is basically the nucleus splitting apart or changing in some way, which causes it to throw out a piece of radioactivity, either alpha, beta, or gamma. So the most basic one is alpha decay. We have here the splitting off of two protons and two neutrons. So we can see it represented here. Obviously, they're not neatly lined up. The nucleus looks a bit more like that, but it allows us to see what's going on. So it only happens once, a bit like popcorn, only popping once, but here we're showing it repeatedly. We've also got it shown here on a diagram. Now, this takes a little bit of explaining. It comes from this diagram here. Now, there's an awful lot going on here. I'll try and make it understandable. Each one of these little squares represents a possible type of nucleus. So along here we've got P for proton, so it's also known as the atomic number, going up to 20 here, so that's calcium, and so on. That's mercury at 80. So in this little section here there are 20 different columns. Now each column represents all the possible isotopes for a particular element, so there are different versions of that element. Now by definition all calcium has 20 protons, but it can have a range of neutrons from, it's a bit difficult to read, but about 15 up to just below 40 there. Now the color over here represents how stable it is. Now we'll look at half-life in a second, but essentially it tells you how likely it is to fall apart. So the black ones here at one extreme are stable. They will remain like that forever. And we really do mean literally forever. At the other extreme we've got here, well, that's a millionth of a second, and that's a 10 millionth of a second, so they don't hang around for very long. So we've got two little blow up sections here relating to these two decays. So the first one here, we said it's losing two protons and two neutrons, so the proton line is here, so we're moving back 2 on the proton line because we're losing two protons, and we're moving down 2 because we're losing two neutrons, so we end up with this diagonal movement here. So we can see boron, this particular version of it, particular isotope, has 10 and it's highly unstable. We can see by the very light color that it's extremely unstable. It's in this region here, and it will decay to a very stable situation here. 1, 2, 3. The third column here is lithium, so 3 protons for lithium there, and we have this alpha particle being fired off, which another way of describing it, it's a helium nucleus, so hence He. Now this top line we can see adds up. 10 is 6 plus 4, which makes sense if we look at the little animation. Nothing's being destroyed, it's just being chipped off. And equally the bottom line adds up. 5 is 3 plus 2, because this is telling us what's happening to the protons. Now slightly weirder and more complicated is beta decay. And what's going on here, we start with the same situation, but here a neutron changes into a proton. We can see that the green circle there changing into a black circle, and it also fires out a very fast moving electron. And again we've got that represented here. It's not quite as neat, but the lines still make some kind of sense. So 10 is 10 plus 0 because there's virtually no mass in an electron, and here we have 5 protons, and now the number of protons increases. Now here this bottom line makes sense in terms of charge, at least. There's a positive 5, positive 6, and minus 1. But as I said, it's not quite as neat as the alpha. And we can see that represented in a third way here. So we've got the animation, the equation here on this little graph. So the number of protons is going up by 1, hence this is moving to the right. And the number of neutrons is going down by 1, hence this is moving downwards. So we have this diagonal to the right movement. Now we did say we'd talk about half-lives. This is a crucial idea in understanding how instability works, how decay works. So we have 3 things here, or 3 ways of representing the same thing. Again, we've got the idea of matter and atoms that are unstable, so they'll decay once in their lifetime. Now the most literal way of representing it is over here on the left. We've got 240 atoms. It'll run again from the beginning. So they are purple when they are undecayed. Here they go. Here's the first half, and here obviously it's not neatly stacked like this. It would be randomly spread out. But this takes 10 seconds. So it takes 10 seconds for the first half to go. It also takes 10 seconds for it to halve again. So it's constantly halving. Okay, so this is our second halving just finishing, and now our third halving starts here. So, and we could carry on, we could halve it, and we could halve it again, and so on. But we're just showing 3 halvings here, and that's the crucial idea, really. It's the halving time. The official name is half-life, and obviously you need to know that phrase. But the time for something to halve is better represents the concept. So as I said, the same idea here is represented in this table. So we've got time in seconds or minutes or years or whatever's the most appropriate unit. We've got half-life, number of half-lives that have occurred, and in the third column we've got undecayed atoms. Now we could just as easily put in here mass or the count, the intensity, because all those things, the less atoms you have or the fewer atoms you have, the lower the mass will be of undecayed, and also the lower the activity. It's the activity you actually measure. Now this green sort of L shape here, sort of rotated L shape, is common to all of these tables, because time is always 0, half-life is always 0, and half-life. So if you draw a table like this yourself, you can just draw that in to begin with, because it's always the same. And again, the crucial thing to realize here is this: we have this halving. So we start with 240, it halves 220, halves again to 60, obviously, and so on. Now in this particular case, as I said, we're going up in 10 seconds. Now the third way of representing it is actually the most common, which is in a graph, but it is obviously an abstraction. It's a step away from the other two, but it is showing the same idea, and it has this characteristic change in gradient. So to begin with, we have a very steep drop-off, and as time goes on it gets less and less. So a key thing to remember is 2 half-lives emphatically do not make a whole life. So half plus a half does not equal 1, and that's confusing only if you don't realize that we're talking about halving time, not half the total. So there we have it, half-life. It's a measure of the stability of a particular type of nucleus. So it has a very long half-life. It can be billions of years, or it can be a billionth of a second, but in either case, if we have a large number, they obey, or they follow this pattern of very predictable halving.